Hi guys, you're welcome to my channel. Today I want to make a quick recap about the concept of friction. To be precise, inclined plane friction. When we talk about frictions on an inclined plane, it is a concept that we need to understand, not just to know it. And I will buttress more on a lot of things that we need to understand about friction. Let's start from this fact that force, when you talk about force, by definition, it is an external agency that tends to change the position of an object or that changes position of an object. Let's start from there. Force does what? Change the position of an object. And whenever an object changes its position in respect to a stationary object, we say the object is in motion. Now, at times, the force might not be sufficient enough to cause the body to change its position completely, but it will tend to change its position. Now, whenever we have what? Motion, we always have a force that will oppose that motion, and that force is what we call a frictional force. Therefore, with the explanation now that whenever force is applied to an object, it always tends to change the position of that object or change the position of the object. Therefore, whenever we apply force to an object, either the object moves or not, there is always a rise in friction. We now have two types of friction. We have the stationary, that is the static friction, and we have the dynamics, or let me just call it kinetic friction. These are the two types of friction that we have: static and kinetic. When you talk about static friction, it is the friction that exists between two surfaces, which we all know already. And kinetic friction is a friction that exists between a moving object and the surface in contact. Are we together now? Cool. Now, if a force causes a body to move, the force that will oppose that motion is what we call kinetic friction. And when a force tends to make an object to change its position, tends to, but it doesn't, that force that will oppose such motion is a static friction, because the body does not move. But because there is application of force, there must be what? Rise of friction. Are we together now? Now let's see something now. Let's say this is a platform. The main reason why I want to recap this topic is because of a question from a Covenant University. And the question seems to be tricky, but to me it's not tricky, so direct. But let's say it is tricky because you can think of it in different ways. So I just want to put light to that in my own understanding. So I would like you to follow the video one after the other so that we can both reach a conclusion. Okay. Now, if I place an object on this table now, anything that makes me to apply a force in this direction, this is an applied force. Either this force is enough to overcome the weight of this body so that the body can be in motion, or it is not able to overcome the weight of this body, that is, this body still remain at rest. As long as we have applied force, there will be an opposing force, which we refer to as a frictional force. Are we together now? You can see that the frictional force is in opposite direction to the applied force. Are we together now? Now, if this body is at equilibrium, that is not moving, because this body cannot move in the vertical direction. Why? Because the weight force, which is the action, is equivalent to normal force, which is the reaction. So these two forces are equal. Therefore, the resultant force along this component is actually what? 0. So motion cannot take place in this direction. Motion can either take place in this direction or in this direction. If the frictional force is greater than the applied force, motion tends to take place in this direction. And if the applied force is greater than the frictional force, it will take place in this direction. Are we together? But if what? The applied force is not sufficient enough to cause this body in motion, then we are going to say the applied force is equivalent to the frictional force. Why? Because the net force on this body will become 0 because it's not moving. Frictional force is equivalent to the applied force, net force is 0. Why? Because they have to move in opposite direction. It has to oppose it. This one wants the body to move like this, friction has to oppose it. Why I'm going through this is because I want you to understand that there is no way you are going to have a frictional force in the same direction as applied force. But the question now is this: is it not possible for frictional force to be in the same direction as the weight force? Yes, it's possible. But it's not possible for frictional force to be in the same direction as applied force, but it can be of the same magnitude. And it will only be of the same magnitude as applied force if the body is not moving. And if the body is not moving, the main reason why frictional force can actually equal in magnitude to that applied force is because static frictional force is depending on applied force until the applied force is greater than the static frictional force. Are we together? Let me quickly buttress more on that. Let's say the mass of this body is 10 kilograms. You can watch my previous video on friction. I'll drop the link in the description below so you can see more detail about static and kinetic. But that is not why I'm here today. Cool. If the mass of this body is 10 kilograms, the weight of the body is mass times gravity. 9.8 times 10, that's going to give us 98 Newton. That shows that the normal reaction of this body is given as 98 Newton. And I would like you to understand that static frictional force is either less than or equal to the coefficient of static friction multiplied by normal reaction. Why? Because it's not constant. The moment the applied force change, the static frictional force would also change. But what about kinetic frictional force? It is equal to coefficient of kinetic friction times normal reaction. Why? Because it's constant. It doesn't change. Either you increase the force or you decrease the force, it remains the same. Now, if you look at something here, let's say I have the coefficient of static friction to be 0.5 and I have the coefficient of kinetic friction to be 0.2. Mind you, the coefficient of static friction is always greater than the coefficient of kinetic friction. We know that already. And if you are still yet to understand, you can check that video I made mention earlier. Cool. Now, that shows that the static frictional force can either be less than or equal to 98 multiplied by 0.5, and that is going to result to 49 Newton. So static frictional force cannot be greater than 49. Anything that makes static friction to be greater than 49 Newton, then this body is already in motion. Are we together? Cool. Then the kinetic friction, that is going to be 98 multiplied by 0.2. And what would that give us? That should be giving us 19 point something, but let me check. 98 multiplied by 0.2, that's 19.6. Are we together now? Cool. By the time this body starts moving, the kinetic friction will always be 19.6 Newton. That's just the case now. Now, if I apply a force of 30 Newton to this body, will the body move? No, it can't, because the maximum static frictional force is 49 Newton. Therefore, what will be my static frictional force here? It will also be 30 Newton because the body is not moving. If I should make my what? Static frictional force in this case to be 49, then the body is going to move towards this direction because this force is greater than the one here. But as the body is not moving, it has to be the same thing. I believe we understand that now. That's not where we are actually going to. Okay? Now let us go to the inclined plane, which is where we actually want to tackle. If I have an object on an inclined plane that is inclined at an angle theta, and this is a body on this. Now, I would like us to examine something. If there is no friction, immediately I place this body on this inclined plane, what will happen? It will slide downward. Excuse me, please. Without seeing this camera. Okay. Okay, sorry. My camera used to stop at times, so I have to just check. Back to class now. So, if there is no friction on this surface, what will happen? This body is said to slide downward. Why? Because of the component of the weight. So, if I place this body here now, the normal reaction of this body is acting perpendicular to this surface. Let me call it R. I like using R instead of Fn. Okay? Now, the weight of the body is also perpendicular to this place now. So, this is mg, which is the weight of this body. Now, if this one is downward like this, and this is also at angle 90, that makes the weight to be the hypotenuse. Are we together now? Now, that shows that the weight force of this body is having two components. The vertical component that is acting in the downward direction, that is in negative y-axis. And it also have what? The x component that is acting in what? In this direction, which is also in negative x-axis. Are we together now? Cool. What is now the magnitude of this horizontal force and what is the magnitude of the vertical force? Let's see. The horizontal component of this and the vertical component of this, for me to get their value in terms of their weight, I need to know the value for this angle. And you will agree with me that this angle is also theta, because this particular point here is 90 degrees to that surface, isn't it? Yes, if that should be the case, I have here and here to sum up to 90 degrees. And if here is what? Angle 90 and here is theta, this place is said to be what? 90 minus theta, isn't it? So, in order for this place to sum up 90 degrees, if here is 90 minus theta, here must be theta. Do we understand that now? So that's why here is theta now. Cool. Now this is the frictional angle, as we all understand. Now if I use what? SOHCAHTOA, I can get the value for this vertical component of the weight to be mg cos theta. And here will be what? Mg sin theta. We actually what? Not looking at all this, but I want us to take it from the basic. Cool. Now, if you look at now, if this body should slide downward, the force that will cause this body to move in the downward direction is just the weight force, because there's no any other force acting on it aside the gravity. And force of gravity is equivalent to its weight force. Now, the weight force along this x-axis is parallel to this one. Therefore, this one is also what? Mg sin theta. So let me call this the force of gravity. Now, if this body now, if there is no friction, I'm coming back to that. What about the vertical component? Since there is no motion along the vertical component, what happens is that what? The resultant force here equals 0. And for the resultant here to be 0, it means the force that is acting downward is equal to the force that is acting upward. Therefore, the resultant, the normal force is also the same thing as the vertical component of the weight force. Are we together, guys? Cool. Now that we are here now, if this body slides downward, how can we get its acceleration? If we assume that there is no friction, then it shows that the body is moving along the x-axis only because we have concluded that here is 0. Now that the body is moving along the x-axis only, the only force acting in that particular direction is the force of gravity. Thus, this one will become mass times acceleration, and this is equal to mg sine of theta. Now, if you look at something here, let's take for instance that this body is not moving. I'll come back to that. But we agree now that it's moving downward. That's why we have that all of the force along the x-axis is just the weight force, which is mg sine theta. And from here we can calculate the acceleration of the body. Ax equal g sine theta, isn't it? So we're done with this. Now let's say the surface is rough, because the question we have to tackle, we are told that there is friction along that surface. Now, if there is friction and the weight force causes this body to slide downward, what will happen to frictional force? It will oppose it in this direction. So frictional force will be moving in an upward direction, that is towards the positive x-axis, and this one is moving towards the negative x-axis. So what will happen? The resultant force along the x component is therefore going to be the gravitational force, because the body is sliding towards this direction. It shows that force of gravity is greater than what? The frictional force. Therefore, I will have Fg to be negative what? Fx. Are we getting this now? Okay, if this should be the case now, this is a kinetic frictional force because the body is moving. Cool. If that should be the case now, this is supposed to be Fk, sorry. So kinetic frictional force. So this will be the mass times the acceleration along this what? X component is equal to the force of gravity, which is mg sine of theta, minus the kinetic frictional force, the coefficient of kinetic friction multiplied by the normal reaction. And then I will have that max equal mg sine of theta minus the coefficient of kinetic friction times normal reaction, which we have to be mg cos of theta. So mass is common. I will have that the acceleration is g sine of theta minus coefficient of kinetic friction, then multiplied by gravity cos of theta. So this will be the used equation for that. Now, what will now happen if the body is moving upward? Now, are we getting the analogy now? You know, we have considered when the body is moving downward now. What if the body is now moving upward? You should know that if the body is moving upward, the force of gravity will always be acting downward, isn't it? Because it's the weight force. The gravitational earth pull on the body is what we refer to as weight. So the weight force will pull it down. Now, the frictional force would also be in the same direction as the weight force, because we are told that the body is moving upward. Since the body is now moving upward, we therefore have that the summation of the forces along the x-axis. Now the body is moving upward, right? You can see both the kinetic frictional force and the weight force, they are now on the same direction, isn't it? Cool. And that will give us, now they are moving towards the what? Negative x-axis, isn't it? That will now make this to be negative kx, and this will become what? Negative what? Mg. They are facing the same direction. So if I add them together, it will still give us what? Negative. That is, if I factorize out the negative, I have Fk plus Fg. We are still in line. Cool. So we have this to be mass times x. Are we together now? Now, this will then become negative the coefficient of what? Kinetic friction multiplied by the normal reaction plus, let me still put the negative because I'm opening the bracket now, the weight force, which is mg cos of theta. Now, this will then become, sorry, this is sine theta. So, the acceleration is now what? Negative coefficient of kinetic friction. Our normal reaction is mg cos of theta minus mg sine of theta. Mass will cancel mass. You can now see that the acceleration is actually what? negative. That is negative coefficient of kinetic friction times gravity cos theta minus gravity sine theta. Now, you will now see that the applied force is actually in an opposite direction to all this. Why? Because what? The result is negative. Why these ones are positive here? Are we together now? So you can see that it is only possible. You know, this is the resultant force along the x component. The resultant force is what tells you the direction in which the body will later move towards. So, because this results now, are we together now? Because what? The applied force now, which is this, we have what? Negative what? Coefficient of kinetic friction times g cos theta. This is what? The acceleration of the body, if the body is moving upward. And the diagram is like this. So if I change the diagram in the other way around, this will become what? Positive. Now what I want to point out here is that you see that the resultant force is always opposite to what? To what we have for kinetic friction. It is only possible for kinetic friction to be in the same direction as the weight force. Are we together now? Kinetic friction can only be in the same direction as the weight force, but it cannot be in the same direction as the applied force, which is what we have seen here. Are we together? I believe you are getting what I'm trying to put out here now. Now, here now, we have not seen the applied force that actually makes this body move upward. And that is why I will now come to these questions that we have at hand now. Now, I believe we have understood this scenario now. We have seen that it's not possible for frictional force to be in the same direction as the applied force, but they can be of the same magnitude, and this will just become a static friction. Now, let's go to the main question now. Now, let's see the main question now. The main question says, determine the magnitude of the minimum horizontal force required to maintain a box of weight 20 Newton when placed on a rough plane inclined at 30 degrees above the horizontal. Now, for us to answer this question correctly, we are given the weight of the object to be 20 Newton. The coefficient of kinetic friction is 0.2. We are now looking for a minimum horizontal force that will not make the body slide. That is, a minimum horizontal force that will cause the body to be at equilibrium. That is what we are looking for. Now, let's see now. If this is my free body diagram, this is where we are actually going. This thing is inclined at an angle of 30 degrees according to the question. Now, this is the object whose weight is 20 Newton. Am I making sense? This is the weight force, 20 Newton now. Now, this is the normal reaction R, which we don't know yet. Now, if this one comes down like this will be the vertical component of this weight force. Let me restructure the diagram better because we still have a lot of things to show here. Okay, this is the free body diagram, 30 degrees, and this is the body whose weight force is 20 Newton. Now, this weight force, this body itself is exerting a normal force that equal R. We don't know the value yet. Now, if I take this one downward like this will serve as the vertical component of this weight force, and here will serve as the horizontal component of the weight force. Abi? Now, the angle here is going to be 30 degrees, which I've proved earlier. Now, if the angle here is 30 degrees, I can see that the vertical component of the weight force is moving towards the negative y-axis, Abi? And the horizontal component of the weight force is moving towards the negative y-axis. Now, if this should be the case, this body now, the weight force acting on this body will cause the body to move in downward direction, isn't it? That is the weight force, Wx. If this body acts in downward direction, are we together now? That is, if there is no what? If there is no friction, if we assume that there is no friction, the weight force will cause this body to move in downward direction. Abi? Now, instead of this body moving in a downward direction, we now what? Applied a force. Let me call that force Fp, or let me call it P. Let's say P is the force that is applied to this body that makes what? Its horizontal component, that is the horizontal component of P, Px, is the horizontal component, prevent this body from sliding downward. You know, this is the applied force now. If this is the applied force that is applied on this direction, what will happen to the kinetic frictional force? It will make the body move downward like this, because the applied force is going like this. The applied force, remember, it can either what? Change the position of the object, or tends to change its position. If it tends to change its position, what will happen? It is going to do what? It is going to be the same value as kinetic friction. Oh, sorry. It's going to be the same value as static friction, because the body will not move. Are we together now? But we are told that this body is moving before. We want to prevent it from moving. That's why we apply this force. But we don't know if this force will actually cause it to move in the other direction or not. Are you getting this now? But we need to maintain the force such that it's going to keep the body at equilibrium. It will keep the body at what? Equilibrium, not to push it backward. But because we know already that it can tend to change or change it, that's why this one arises. Are we together now? Now, if that should be the case, we'll see that this now is acting like this, and this one is acting downward, which we agree. But we want this one, this particular force here, to be of the same value with this, so that this body will be in total equilibrium. That's the case. The weight force is already acting downward. If the weight force will overcome this applied force, this body will sweep downward. There's nothing we can do to prevent the weight force. We need to consider it. It's pushing the body downward. We want this what? This particular body to prevent it from moving downward. That's why we are applying this in this direction. And since this is applied force will cause what? A frictional force to rise up. That is why you see this frictional force acting downward. The frictional force cannot be in the same direction as this, because if the frictional force should be in the same direction as the applied force, then we are not going by the definition of friction to oppose the motion of an object. Do we understand this now? Let's say we don't have this applied force and this body is on this plane now. We don't want to prevent it. Are we together now? If the weight force causes this body to slip downward, the frictional force will oppose it. And that's why I showed the previous one explanation on this. But now that we apply this force now, the frictional force is to overcome this force. Because this force now has overcome the weight force. It's not pushing the body upward now. We want this body to be at equilibrium. So we are in need of a force which is going to act in this direction and is going to be of the same magnitude as kinetic friction. That is just the question. Are we together now? We need the force that will make this body to be at what? Static station. And that force must be equivalent to what? To kinetic frictional force. That will now make kinetic frictional force to become what? A static friction. But we cannot consider it to be a static now, because we consider this body that the weight force is causing it to move downward. This force we are applying now, we don't know if it's going to push it up, but our aim is to make this body be at equilibrium. So now, how can we do that? Now let's get that cleared now. We have to resolve this component also. If you look at this force P, it's also having two components, the horizontal component and the vertical component. its vertical component is also acting in a negative what? Direction. But its what? Horizontal component is acting towards the positive x-axis. Why? That of the weight force. The weight force, if you look at the horizontal axis of the weight force, is acting in opposite direction, that is in a negative direction. While its vertical axis is also acting in what? In negative direction. And the normal force is acting in a positive y direction. Remember that we don't know the value for the normal force, isn't it? But we should be able to determine that as we move now. Can we go on? Yes. Now I will resolve the component of the forces that I have here, that is the weight force and the applied force. So for the vertical component, summation of the forces at the vertical component is going to be the normal force. Now the weight force is acting in the negative direction. That will be negative what? Wy. Then the vertical component of the applied force also is also negative. That is what? Py rather. It's supposed to be Py, pardon me. Okay, so if this should be the case now, since the body is not moving along this axis, that shows that all these forces, they are actually equal to what? 0. So this can be 0. Now our R, which is the normal force, we don't know yet. Then our W, this is going to be minus what? Minus the weight force in the vertical axis. The weight force in the vertical axis is going to be what? Is going to be given as the weight sine of 30 degrees. Okay, sorry, that's a mistake. It's supposed to be cos. That will be 20 cos 30 degrees. Are we together? Cool. Then minus the vertical component of this. Remember that this one also, now the normal reaction R is therefore going to equal, this will come to the other side. I'll have 20 cos 30 degrees plus P sine 30 degrees. So from here now, I have that 20 cos 30 degrees. That should give us what? So R equal, this should be 17.3 if I'm not mistaken. Let me check. 20 cos 30. So that's 17.3 plus P sine 30 degrees. So let me call this one my first equation. So if I call this my first equation now, I can then consider the horizontal component. So the summation of forces along the horizontal component. This is where the work lies now. And I will have that for the weight force. The weight force is moving in the negative x direction. Likewise, the frictional force also, right? Now, but the applied force horizontal component is towards the positive axis. So I will have that Px, which is the horizontal component of P, minus the frictional force, then minus the weight force in the x direction. Are we together now? So the summation of f of x is there equal what? P cos of, because the horizontal component of this will become cos, P cos 30 minus the kinetic friction is given as the coefficient of kinetic friction multiplied by the normal reaction minus the weight force. That's going to give us 20 Newton sine 30. 20 sine 30 degrees. Now, this is where we now need to apply, what we are even arguing about, that we are like thinking that kinetic friction is actually going to be in the same direction as the applied force so that the body can stop. No, that is not going to be the reason for the body to stop. That is for the body to stop reason. The only reason for the body to stop moving is for the resultant force on that component to be 0. If the resultant force on that component is 0, it shows that there is no motion along that component. And if there is no motion along the vertical component also, that shows that the body is at equilibrium. So if a body is at equilibrium, the resultant force acting on it must be 0. That is what we are going to. If this body is in motion, this one can never be summed to 0, because this one will be greater than this. But in this case now, this now is equal to this. Are we together now? I believe we are meeting at a point now. Cool. Now, this will become 0 now. If this one should become 0, I will then have that P cos 30 is therefore equal the coefficient of kinetic friction multiplied by the normal reaction plus 20 sin 30, that will give us 10. Okay, so permit me now. Okay, I think I still have more space here. Good. I'll call this one equation 2. But before I call this now equation, okay, I can call it equation 2 now. What I want to do now is, I want to use this equation 1 to rewrite equation 2. So how can I do that? To use equation 1 to rewrite equation 2, equation 1 is equal to R. So anywhere I find R in equation 2, I'll replace this with that. So I will therefore have that P cos 30 is equal to the coefficient of kinetic friction we are given to be 0.2 multiplied by R, which is 17.3, plus the P sine 30, P sine of 30 degree, plus 10. Remember, we are looking for the value of P. So we need to make all P's to be in one side. Therefore, I will have that P cos 30 equal 0.2 multiplied by 17.3. That will give us 3.46 plus 0.2p sine 30, then plus 10. So this one now can cross to the other side. I have what? P cos 30 minus 0.2p sine 30 equal 13.46. Cool. P is common. If I factorize it out, I therefore have cos 30, that should give me 0.866 minus 0.2 multiplied by 0.5. That will give us 0.1 equal 13.46. So P now is equal to 0.866 minus 0.1. That will give us 0.766. So I have 13.46 divided by 0.766. So what will I have? 13.46 divided by 0.766. So the value for P is going to be 17.57 Newton. So this is the minimum force that will make this body to be at equilibrium, so that there won't be motion on the x-axis, as there's no motion on the vertical axis. And I believe by now all what we are arguing about